The original work energy theorem, I like to call the work energy theorem version 1.0. States that the initial kinetic energy plus the total work done on the system equals the final kinetic energy. This version is usually used when the system being analyzed consists of only one object, like the 2 kilogram box. The work energy theorem version 2.0 states that the initial kinetic energy plus the initial gravitational potential energy plus the initial elastic potential energy plus the non-conservative work done equals the final kinetic energy plus the final gravitational potential energy plus the final elastic potential energy. This is usually used when analyzing a system with 2 or more objects in it. For example, the wall and the spring and the object, all of that being our system. Today's lesson is all about showing the derivation between the first version and the second version. The question is, how can the work energy theorem used for 2 object systems be derived from the theorem used for 1 object systems? All right, so here we go. We start off with version 1.0, the initial kinetic energy plus the total amount of work done equals the final kinetic energy. But this total work can be broken up into 2 categories. The work done by the conservative forces and the work done by the non-conservative forces. Recall the work done by the conservative forces is independent of the path taken from the initial starting point to the final ending point, whereas the non-conservative work does depend on the path taken from the initial point to the ending point. Now, this conservative work, in the past, we showed that the work done by the force due to gravity was conservative work. Well, another example of conservative work is the work done by the spring force. Now, recall, the work done by the force due to gravity turned out to be equal to the negative change in the potential energy due to gravity, where the potential energy due to gravity equals mgh. Similarly, the work done by the spring force is equal to the negative change in the potential energy stored in the spring, where the potential energy stored in the spring is equal to 1/2 kx squared. So if we make those substitutions in to our original equation right here, we end up with the initial kinetic energy plus the work done by the force due to gravity plus the work done by the spring force plus any non-conservative work done equals the final kinetic energy. But the work done by the force due to gravity is equal to the negative change in the potential energy due to gravity plus the work done by the spring force equals the negative change in the potential energy stored in the spring. And then we have the work done by the non-conservative forces, and all that added up equals the final kinetic energy. But then I could replace the change in potential energy with the final gravitational potential energy minus the initial gravitational potential energy. Likewise, I can replace the change in the elastic potential energy. I still have this negative sign here, so that comes down right there. The change in potential energy due to the spring is equal to the final potential energy due to the spring minus the initial potential energy due to the spring. And then I still have to add any non-conservative work done, and that all equals the final kinetic energy. Now I'm going to distribute those negative signs. So the initial kinetic energy plus the negative of the final gravitational potential energy plus, but then when I distribute the negative sign over here, I get a positive potential energy due to gravity initially. Likewise, when I do the same thing over here, I distribute that negative sign, I get the final potential energy stored in the spring, but that's negative, plus when I distribute that over here, that negative sign, I get positive potential energy stored in the spring initially. Don't forget to add the non-conservative work, and that equals the final kinetic energy. And then when I slide and add these two terms over to the right hand side, I end up with the initial kinetic energy plus the initial gravitational potential energy plus the initial elastic potential energy plus the non-conservative work done equals the final kinetic energy plus the final gravitational potential energy plus the final elastic potential energy. Notice these three terms, sometimes I refer to them as the three musketeers. They make up the total initial mechanical energy. And these three terms over here, they make up the total final mechanical energy. And if there isn't any non-conservative work, we would have conservation of mechanical energy. In summary, if we just choose to analyze the box, and that's our system, then we would use the initial kinetic energy plus the total work done equals the final kinetic energy. And the work done would be the work done by the spring force as it pushes that box out to the right. But another route to go is to analyze both the wall, the spring, and the mass as our system. And if we do that, we'll use the initial kinetic energy plus the initial gravitational potential energy plus initial elastic potential energy plus the non-conservative work done equals the final kinetic energy, plus the final gravitational potential energy plus the final elastic potential energy. And in this particular problem, there wouldn't be any non-conservative work. The work done by the spring force is taken care of by these potential energy terms. In this particular problem, the object started off at rest. There isn't any altitude change from the beginning to the end. So it's just a matter of the initial elastic potential energy being equal to the final kinetic energy. 1/2 kxi squared equals 1/2 mvf squared. When possible, choose the two-mass system and use the bigger equation. It turns out to be simpler, easier. Good luck.